Hello friends, I am Mr. Adeesh Deshpande from Fergusson College. Let us start the discussion of P block elements in that group 16. Students, last year we studied the periodic table in that there are four blocks: S block, P block, D block and F block, of which let us find out the meaning of P block elements. We already studied this, so let us revise. Elements in the atoms of which the differentiating electron enters p orbitals of the outermost shell. So differentiating electron is the last electron that enters into the atom. When it enters p orbitals of the outermost shell, then that element is called as p block element. Since maximum of 6 electrons can be accommodated in a p subshell, 13 to 18 in the p block. So there are total 6 groups which are present in the P block, of which we studied group 13, group 14 and group 15 in the last year's syllabus. This year we are going to discuss group 16, group 17 and group 18 elements. Now what are group 16 elements? Group 16 elements are oxygen, sulfur, selenium, tellurium and polonium. So here are their symbols with the atomic numbers are also given, as this group starts with oxygen. The family is called as oxygen family, or these are the members of group 16, which is also called as oxygen family members. The first four elements are called as overforming elements. The word used is chalcogens. This is because a large number of the metals found in the Earth's crust are in the form of oxides and sulfides. And this oxygen and sulfur both are the members of group 16, and so these family members are also called as chalcogens. So some of the examples are given: Cu2O, CuO, Ag2S, ZnS, FeS, etc. So these are our group 16 elements or oxygen family members or chalcogens. Occurrence. Oxygen is the most abundant element on Earth. As we know, it forms almost 21% by volume of air. That is, it also forms 46.6% by mass of Earth's crust. Now sulfur forms 0.034% by mass of Earth's crust. Sulfur occurs in the combined form as sulfates. So some of the examples are given: gypsum salt, Epsom salt, barite, etc. And it also forms sulfides, or it also occurs in the combined form as sulfides. So examples are zinc blende, galvanized sulfide of lead, copper pyrites, that is mixed sulfide of copper and iron. Then selenium and tellurium occur as metal selenides and metal tellurides in the sulfide ores. So in the sulfide ores itself, selenides and tellurides are associated. Now polonium is radioactive and it occurs as a decay product of thorium and uranium. So this is how these oxygen family members occur in the nature. Now electronic configuration. Valence shell electronic configuration is Ns2Np4. That means 6 electrons are present in the valence shell. So all these elements, they are short of 2 electrons to attain the nearest noble gas configuration. So here are the elements, their atomic numbers and their electronic configurations which are given. So oxygen, atomic number 8, configuration is helium core 2s2 2p4. Sulfur, atomic number 16, configuration is neon core 3s2 3p4. Selenium, atomic number 34, configuration is argon core 3d10 4s2 4p4. Tellurium, atomic number 52, configuration is krypton core 4d10 5s2 5p4. And for polonium, atomic number 84, configuration is xenon core 4f14 5d10 6s2 6p4. So if nth shell is the outermost shell, then the general valence shell configuration can be written as ns2np4. And so 6 electrons are present in the outermost shell. So they require just 2 electrons to complete the octet. Now let us discuss some of the atomic properties. In that, very first is atomic and ionic radii. Now these atomic properties are studied last year when we studied periodic table. But with respect to this particular group, now we are going to discuss these atomic properties. So atomic and ionic radii. Atomic and ionic radii increase down the group due to the addition of a new shell at each successive element on moving down the group. So this trend we already studied on moving down the group, as there will be always introduction of a new shell and therefore effective atomic radius increases. Now atomic radii of group 16 elements are smaller than those of corresponding elements of group 15. This is because of increase in the effective nuclear charge. So these are the trends in atomic and ionic radii. Now second periodic property is ionization enthalpy. So ionization enthalpy decreases down the group due to increase in the atomic size. So this we already studied, that there is always inverse relationship between atomic size or atomic radius and ionization enthalpy. If atomic radius is greater, ionization enthalpy is smaller, and vice versa. Now as we move down the group, size of the atom increases, so ionization enthalpy decreases. Now across the period, if we consider ionization enthalpy, then this point one has to remember. Just to go through the electronic configuration of group 16 elements and group 15 elements. For group 15 elements, outer configuration is ns2np3. So in this case you will find that s orbitals are filled, or s orbital is filled completely, and each p orbital contains 1 electron each. So this is very stable and symmetrical configuration. Now comparing this configuration with the configuration of group 16, we will find that the last electron starts pairing up with one of the electrons in np orbital. And so this configuration, that is configuration of group 16 elements, is less stable and less symmetrical. So as a result of which, elements of group 16 have lower ionization enthalpy values compared to those of group 15 in the corresponding period. This is due to extra stable half-filled p orbitals electronic configurations in the elements of group 15. So this is the point that one has to remember. The next periodic property is electronegativity. Electronegativity decreases down the group due to increase in the atomic number. Next to fluorine, oxygen has the highest electronegativity value amongst all the elements. So this is also one of the important point as far as oxygen element is concerned. Oxygen is the second most highest electronegative element in the periodic table. Now, electron gain enthalpy as the next property. Because of the compact nature of oxygen, it has a less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. Now, why this is so? Because oxygen is more electronegative than sulfur. Oxygen has the smallest ever atomic size in the group. So in oxygen, electron cloud is spread over a small region and the charge density is higher. Due to high electron density, oxygen atom does not accept incoming electron easily and therefore has a less negative value of electron gain enthalpy. The decrease in the electron gain enthalpy from sulfur to polonium is due to decrease in the electronegativity. So this trend we have to remember. As far as oxygen element is concerned, it has less negative electron gain enthalpy. Now let's consider some of the physical properties in that physical state and molecular structure. So we know that oxygen is a gas and all other elements are solids at ordinary temperature. Oxygen has ability to form p-pi multiple bond. The p-pi overlapping between two oxygen atoms lead to the formation of oxygen-oxygen double bond. So here is the diagram which represents double bond between two oxygen atoms. As we know that these elements are short of two electrons to attain the nearest noble gas configuration, and therefore by forming such double bond, both the oxygen atoms acquire 8 electrons in the valence shell. Intermolecular forces between oxygen molecules are weak van der Waals forces. Therefore, oxygen exists as diatomic gas at ordinary temperature. The higher elements, sulfur and selenium, are unable to form p-pi bonds due to their larger atomic size. Therefore, these elements do not occur as diatomic molecules. So this is the variation between oxygen and other elements of group 16 elements. Oxygen exists as a diatomic gas, but remaining elements do not occur as diatomic molecules. Now, sulfur and other heavier elements link their atoms by single bonds to form polyatomic complex molecules. So this is quite interesting that sulfur and selenium exhibit this property. So sulfur molecule has 8 atoms joined together through single bonds to form a puckered ring. So this is the puckered ring structure of sulfur, where you will find that there are 8 sulfur atoms and each sulfur atom is covalently bonded with the 2 other sulfur atoms, and thereby it forms a puckered ring which is also called as a crown shape. Selenium also exists in this particular puckered ring structure. So sulfur and selenium exists as S8 molecule or Se8 molecule. In heavier elements, the polyatomic molecules are held together by strong van der Waals forces, hence they exist as solids under ordinary conditions. Now next property is metallic character. Metallic character increases down the group. Oxygen and sulfur are non-metals, as we know. Selenium and tellurium are metalloids and polonium is a metal. So metallic character increases as we proceed down as we move down the group. Now the next property is melting and boiling points. So melting points and boiling points increase on moving down the group due to increase in the atomic number. Polonium possesses lower melting and boiling points than tellurium due to inert pair effect. Students, last year we studied inert pair effect. So if we recall this inert pair effect, you will understand that polonium possesses lower melting and boiling points than tellurium. The s electrons of polonium are less readily available as compared to tellurium. So this is the part of inert pair effect. Therefore, intermolecular van der Waals forces are weaker in polonium and it has lower melting points and boiling point as compared to tellurium. Now all elements of group 16 exhibit allotropy. So we studied allotropy. So allotropic modification or allotropic forms are nothing but that element exhibits the same chemical property, but physical properties are different. So such forms are called as allotropic forms. Group 16 elements exhibit allotropy. So here is the table which gives you allotropic forms of all these elements. So sulfur in all these elements exhibit maximum allotropic forms. So these are the allotropic forms of group 16 elements. Allotropes of sulfur. We are going to study some of the allotropic forms of sulfur. So it exhibits numerous allotropic forms. However, rhombic sulfur, which is also called as alpha sulfur, and monoclinic sulfur, which is called as beta sulfur, are the most important allotropes of sulfur. So here is the table which gives you the comparison between rhombic sulfur and monoclinic sulfur. So in the first column, you will observe some of the characteristic properties, and accordingly alpha sulfur and beta sulfur, the description is given. So these are the two important allotropic forms of sulfur. Now these are the structures of rhombic sulfur and monoclinic sulfur. So on the right hand side, you will find that rhombic sulfur above 94.5 degrees centigrade changes to monoclinic sulfur, and below 94.5 degrees centigrade, monoclinic sulfur forms rhombic sulfur. So overall, crown-shaped structure or puckered ring structure is shown in this particular diagram. Now, anomalous behavior of oxygen. You know that the first element in all these families exhibits certain different characteristic properties than the other members of the same family. So in group 16 elements, oxygen is the first member which exhibits some of the properties which are different from other members. And so this behavior is called as anomalous behavior. So oxygen differs considerably from other elements of group 16 in several properties. This anomalous behavior is due to the following reasons: small atomic size of oxygen, very high electronegativity of oxygen, and absence of vacant d orbitals in the valence shell. Now, which are the properties exhibited by oxygen? Those are different from that of the other elements. The first is atomicity. Oxygen is diatomic while others are polyatomic. That is S8, Se8, puckered ring structure as we studied earlier. Then magnetic property, oxygen is paramagnetic while other elements are diamagnetic. Then oxidation state, oxygen shows oxidation state of -2 in most of the compounds. Due to the absence of vacant d orbitals, it cannot exhibit higher oxidation state. The other elements of the group can exhibit -2, +2, +4 and +6 oxidation states. This we are going to discuss in the earlier part. But this is a point of difference between oxygen and other elements of the group. Then hydroids. Hydroid of oxygen is water. So it is a liquid at room temperature, while hydroids of all other elements are gases. For example, hydroid of sulfur is H2S. all of us know that H2S is a gas as we are using that in the laboratory. Then common covalency of oxygen is 2. In rare cases, it is 4. But for other members of the group 16, covalency can exceed 4. So these are some of the points of differences where oxygen exhibits different properties than the properties exhibited by other members of the group, and so it is called as anomalous behavior of oxygen. Now let's discuss some of the chemical properties. In that, first is oxidation state. Now valence shell electronic configuration, as we studied, is Ns2Np4. So it can attain noble gas configuration by gaining 2 electrons forming E2 minus ion. E represents any group 16 element. Or there is another possibility that noble gas configuration can be achieved by sharing 2 electrons forming 2 covalent bonds. So either there is a formation of 2 covalent bonds or by gaining 2 electrons forming E2 minus ion. Thus, these elements show -2 and +2 oxidation states in their compounds. Now let us consider oxygen first. It is highly electronegative and it shows common oxidation state as -2. One exception you have to consider: in oxygen difluoride, its oxidation state is +2, and in all peroxides, oxidation state is -1. Considering these exceptions, if you go through any compound of oxygen, you will find that oxidation state is -2. Now other elements exhibit +2, +4 and +6 oxidation state. In that, more common is +4 and +6. So here is the chart that can give you how +4 and +6 oxidation state is obtained in case of sulfur. So ground state configuration of sulfur is given 3s2 3p4. So if sp3 hybridization occurs, then tetrahedral atom exhibits +2 oxidation state. Now, if you consider first excited state of sulfur atom, then you will find that configuration is 3s2 3p3 3d1, and by sp3d hybridization, this sulfur atom can exhibit +4 oxidation state. Similarly, in the second excited state of sulfur atom, configuration is 3s1 3p3 3d2, and by sp3d2 hybridization, sulfur can exhibit +6 oxidation state. So stability of +6 oxidation state decreases down the group. Stability of +4 oxidation state increases down the group due to inert pair effect. Bonding in +4 and +6 oxidation states are covalent. Now let's consider reactivity towards hydrogen. All group 16 elements form hydrides having formula H2E. For example, H2O, that is water, H2S, hydrogen sulfide, then H2AC, H2TE, and H2PO. So all elements exhibit these hydrides. Oxygen also forms another important hydroid, which is H2O2, hydrogen peroxide, as we know. All these hydroids have angular geometry and are formed by sp3 hybridization of central atom. So oxygen atom undergoes sp3 hybridization, sulfur atom undergoes sp3 hybridization, and then it forms these hydroids. Now water is a colorless, odorless liquid. H2S, H2AC, H2TE, and H2PO are all colorless, bad smelling, poisonous gases at ambient conditions. This we know. H2S, the smell is known to us, so it's always bad smelling and poisonous gas. Now some of the properties of these hydrides. The first is acidic character of the hydride. EH bonds present in these hydrides are polar and dissociates in aqueous solution to produce H plus ions. Hence, these hydrides act as acids. The hydrides of group 16 elements are weakly acidic. Due to the decrease in the bond dissociation enthalpy of EH bond down the group, acidic character increases. So, the acidic strength of these hydrides increases in the order H2O less than, H2S less than, H2SE less than, H2TE. So, this order is quite important. This is the order of acidic character of the hydride. The next property is thermal stability. The thermal stability decreases in the order. Water is maximum stable, then H2S, then H2SE, then H2TE. On moving from water to H2TE, the size of the central atom increases and therefore the tendency to form EH bond decreases. As EH bond becomes weaker, thermal stability of the hydride decreases from H2O to H2TE. Then reducing character of the hydrides. Except water, all other hydrides of the elements of group 16 act as reducing agents. The reducing character depends upon thermal stability. Lesser the thermal stability, greater is the reducing power of the hydride. Since the thermal stability of the hydride decreases on moving down the group, reducing power of the hydride increases from H2S to H2TE. So H2S is the weakest reducing agent, but H2TE is the strongest reducing agent. Now let's consider reactivity towards oxygen. All elements of this group form oxides of the type EO2 or EO3, where E is any group 16 element. EO2 type oxides. So O3 and SO2 are gases, where SeO2, selenium dioxide, is a solid. They are acidic in nature and react with water to form acids. So, sulfur dioxide reacted with water forming H2SO3, that is sulfurous acid. Likewise, selenious acid can be formed. Reducing property of dioxide decreases from SO2 to TeO2. So, SO2 is reducing agent while TeO2 is oxidizing agent. Now EO3 type of oxides. So EO3 type oxides are also formed by sulfur SO3, we know, then selenium SeO3 and tellurium TeO3. They are also acidic in nature. They dissolve in water to form acids. So selenic acid forms H2SeO4, telluric acid form H6TeO6. So students, in this class, we saw group 16 elements, some of the atomic properties, physical properties and chemical properties. Thank you.